Hello, my fellow Center for Acoustic and Vibration members. It is really my pleasure to have a chance giving you a brief introduction of the various activities of the sound and vibration research at the Hong Kong Polytechnic University. And my name is Randolph Leung. Okay, and I'm the Deputy Director of the Consortium for Sound and Vibration Research, which is directed by Professor Chen Li. We both are coming from the Department of Mechanical Engineering, the Hong Kong Polytechnic University, Hong Kong. Okay, so before I start the brief introduction, I just want to show you some nice picture about our city, Hong Kong. Okay, now in fact, Hong Kong is a very small city, okay, which is very small, only around more than 1,000 square kilometer. And however, okay, Hong Kong has a very strong international exposure, not only for its international financial center status, as well as we have a very beautiful, attractive, and nice scene, okay, across the harbour of Hong Kong. We call Victoria Harbour. Now, as you can see, from this picture, actually, we have a lot of beautiful lights are on in the night time, and in fact, okay, the people of Hong Kong are still very active in the night. Okay, just allow me to say a bit about our university, the Hong Kong Polytechnic University. In short, we just call it PolyU, okay? And PolyU has a very long history. It was established in 1937 as a kind of trade school and then technical college, and then polytechnics. And we became a university in 1994. And PolyU is the largest tertiary institution in Hong Kong with more than 30,000 students. With such a long history, it's no surprise we have a large pool of alumni of around 310,000 alumni. We altogether have more than 200 taught programs at the bachelor, master, and the doctoral levels. And all these taught programs are delivered by 26 departments or schools under 8 large faculties. And certainly, we are coming from the Faculty of Engineering. Okay, just to say a bit about the research Foci in ME. There are 4 pillar research areas in our department. They are the integrated product development, combustion and pollution control, fluid structure interaction, as well as the sound and vibration. And actually, the activities in all these 4 pillar research area support a broader research area with a stronger bias application, that is in aeronautical engineering. Okay, so that's we can just leverage, okay, the academic know-how to the real application to meet the needs in the actual needs in the industry. So let's say a bit about the Consortium for Sound and Vibration Research. In short, we call CSVR. It comes with a long history too. In fact, it started off as a research center for noise abatement and control in the beginning of this century. And you know, the university recognized our achievement and our academic excellence. They provided some extra funding to set up the CSVR in 2007, and which we can see that this as a CSVR is the kind of academic excellent units of the PolyU. And in fact, we have a pretty strong academic strength, in the CSVR. We have different faculty members working in different areas of the sound and vibration. Okay, now that's just I can show you here in the list, and you can see that basically we cover almost all kinds of sound and vibration research areas in the basic general as well basic general works as well as the in the area of application of high values. Now, so just let me tell you a bit about the rationales of the CSVR. Is certainly is like other research units in acoustics and vibration. Certainly, they put the focus on the activities of the noise and vibration. However, just looking at the noise and vibration as well as the relevant problems around us in Hong Kong and worldwide. Okay, we also pay extra attention to the flow, and we believe that the three major areas, say noise and flow and vibration, they are interrelated. Okay, in any practical noise vibration problem, and so that's why we pay extra attention to the interaction between these three areas. And we hope that we can develop the new knowledge, new discovery, and advanced know-how, so that we can make use of them for making the acoustic environment around us more comfortable. And we hope that we can help develop more new ideas, so as to increase the competitiveness of the industry product for our Hong Kong manufacturers. And certainly, we also want to develop the new enabling technology, for the future sound and vibration related applications. And in order to achieve the goals that we just mentioned, so practically, we roughly take part in the research in the following 7 themes. We just give them the orders A, B, C, D, E, F, G. Basically, they all cover all the major activities we are taking part in. Say aeroacoustics and structural acoustics, building and environmental noise, computational methods for sound and vibration research, dynamics, vibration and control technology, embedded structural health monitoring, fluid structure, sound interaction, as well as the general acoustics. Now, in fact, our many years of efforts are well recognized by the government funding agency, as well as the industry in Hong Kong, as well as the region around us. Now, in fact, we got a lot of fundings, from the government through our RTC, of Research Grants Council in Hong Kong, which is similar to the NSF in the US. And we also get some funding from the NSF China for our foundation research. And we were also very successful in securing the projects through ITF, Innovation and Technology Fund, which help us to support us to implement our ideas into real applications. And certainly, from time to time, we got a lot of requests for help from the industry, as well as the government departments on the noise and vibration problems, as you can see from the list okay, with purple, okay, basically all those major brand as well as the major, let's say, public utility, as well as the transportation firms, manufacturer also have been, okay, we have a very constant contact with them, okay, so that we can get more support and to help them. And at this stage, just to show some examples, in fact, the full list is pretty long, that I cannot put them all into this single page. But at least you can get some idea what kind of projects that we have been working on and how we make the use of our knowledge, okay, to advance the sound and vibration research competency achieved in Hong Kong. Okay, just a brief, okay, of the research facilities for our sound and vibration research. We have the largest echo chamber in Hong Kong. We have a state-of-the-art phonography system for the sound source identification and localization. We have an advanced laser vibrometer that allows us to measure the vibration at any point in 3D. We have a decent reverberation chamber for the study of a building acoustic with a different renovation or interior features. We have a acoustic wind tunnel that helps us to study the air acoustic as well as the flow-induced vibration. And not so. We also have quite a lot of state-of-the-art of the simulation software like the system here for our for the calculations of our project. We also have a kind of a decentralized sensing probes, okay, for our structural health monitoring projects. We also have full facilities, okay, for carrying out the large-scale noise and the vibration measurement. That's like the one at the center that you can see that we measure the traffic noise variation, okay, due to the airport railway, and also from at the right, okay, we study the vibration characteristic of aircraft fuselage. And well, our expertise are also recognized, okay, not only for the industry, the applications, or in the city scale around Hong Kong, and actually our director, Professor Chen Li, okay, he was also involved, okay, in making use of his vibration or vibroacoustics, okay, know-how for the better understanding of the mechanics and space environment mechanics, okay, in the space environment engineering, and he could establish a fund lab, okay, with the China Space Agency, okay, for a project, okay, so that we just extend our capability, okay, to for the study, okay, of certain more vibration problem, okay, that's a figure for the applications in the space environment. Okay, up to this point, I just gave you a kind of a very brief idea, okay, of our CSVR activities, and here I like to just tell a little bit more of the current research projects our CSVR colleagues are working on. Well, the first one is the kind of the project okay, from Professor Li Chen. Okay, Li Chen, Professor Chen is working on several major areas. Now, the first area is the guided wave-based structural health monitoring techniques. Essentially, he wants to make good use of the LEM waves as well as the acid waves, okay, for for developing advanced technology for structural health monitoring. Essentially, he would just develop a very strong basic understanding for all this for the technology, and then develop the realization using extensive numerical method, essentially finite element method, and then finally he move on to apply the idea into the real engineering situation, like the aircraft panel or train muscle applications. And all this, his work is well recognized by the industry. The second area that's for Professor Li Chen is the vibration-based structural health monitoring. Okay, and essentially, basically, again, he would just first put the focus on the local dynamical behavior of the structure, and from which he developed the further extended application, like the technology for the application, say the model identification, the detection, development of a multi-scale model, as well as finding out some new applications. Like basically, in this slide, you can just you can get as a brief idea, okay, what kind of activities that he has been working on in all these four major areas for vibration-based structural health monitoring. And recently, he has been heavily involved in the research of the acoustic pulse, okay, ABH, okay, so that's he wanted to advance this the acoustic black hole idea in the many different structural vibration as well as the micro acoustic application. Okay, his work involved system analysis, modeling, wave visualization at the certain application. Okay, and so there's a lot of possibility. Okay, with acoustic back ABH. And finally, okay, he is also involved on the quite a lot of work in materials, and in particular, he is interested in the topological optimization. Okay, he wants to make use of the theory of topological optimization, so that we can design, okay, the kind of materials with desirable properties. So here just some snapshots showing the different works in the elastic material that he's working on, and he also have some works on the acoustic material. Okay, that's very interesting. Now that what's next, okay, is mainly the research in the area of the flow-induced noise and vibration, and that this area is mainly led by. Okay, now recently, okay, we have been working on some interesting projects that we aim to leverage the flow-induced vibration, okay, to a much more flow application. Now, right now we are trying to see whether we can make use of the flow-induced vibration of an elastic panel that is installed on the airfoil surface, so as to achieve an overall reduction of the airfoil itself, the tonal noise. Okay, in fact, this idea, okay, we carry out extensive numerical analysis with a direct error acoustic simulation, and we found out that we can achieve a reduction up to 3 dB without any degradation in the aerodynamics. Okay, which is very different from other existing ideas. Okay, that the aerodynamic performance has to be punished. And then we further on develop a kind of reduced order modeling technique we call the perturbation evaluation method, so that it allows us to develop different elastic panel design for the airflow total noise reduction in a much more effective and quicker manner. And that's a kind of a PEM method basically requires only 10% of computational time of this corresponding direct area acoustics simulation. And then based on with this kind of very effective design tool, we are able to push this idea for, deeper, and to see whether we can find out a design configuration with multiple panels, such that we can get more noise reduction. So far, our calculations show that we can achieve a total noise reduction up to 9 dB with only 2 panels at the optimal positions. Another area, on the flow-induced noise and vibrations are mainly in developing a direct simulation model for the prediction of the noise control effectiveness with a porous liner in a flow duct. And the idea is the reason why we want the direct simulation rather than the impedance-based model is that in fact in the flow duct, the flow actually will get into the air, the porous liner, and come out, which may cite some flow instability. That will amplify the noise over a certain range of the frequency. And that kind of instability, the hydrodynamic instability, is very difficult to predict. And that's why we want to get a better understanding with a kind of direct area acoustic simulation technique, and we want to find out the root cause for this hydrodynamic instability. Another direction is that it involves the noise control in a duct, with an elastic panel liner. In fact, we really want to make it's similar to the previous slide. We want to just make use of an elastic panel liner, install it inside a flow duct, and so that we can achieve a very high transmission loss, of the noise through the ducts. And in fact, at the certain design, certain elastic panel structural property together with the specific design of the cavity behind the panel, we are able to achieve a very remarkable acoustic absorption, over a broad range of the frequency, which is pretty desirable. And in particular, for this kind of elastic panel liner design, we don't suffer from the extra pressure loss, to the duct flow. And so it is a kind of interesting direction to push through. Now, the next area is on the nonlinear attributes of the elastic wave, which is the focus on the Professor Su, Zhongqing Su. And his work is mainly on the fundamental study of the nonlinear behavior of the elastic wave on thin structure, and then trying to make good use of this behavior for the advanced for developing the advanced technology for structural health monitoring. This is the one page that he provides me. Is on he works on understanding the content acoustic nonlinearity, the CAN, using thermal sensitivity of CAN to enhance the robustness of the nonlinear ultrasonic based damage evaluation. Basically, the major target here is to get to know the final way to capture the fatigue-induced crack, okay, and then to see when to study the crack propagation behavior. Now, there are several objectives in this area. He wants to know the physical interpretation of acoustic nonlinearity in both 2 and 3D. Okay, and then he goes on to evaluate the fatigue crack orientation using the crack-induced can. And at the same time, he developed a fundamental understanding of the thermal sensitivity of can, so that eventually he can make good use of the thermal sensitivity to enhance robustness of the nonlinear acoustic phase damage characterization. Now, here the acoustic phase, usually he is talking about the acoustics in the ultrasonic regime. Okay, now so these are the different slideshow to show some idea, and it seems that he can get a really good progress, and then he probably you will see that his ideas are appearing in the market. Okay, now and then looks okay. Just allow me to tell a little bit about the research area of Dr. Jie Zhu and Dr. Cao Liu. Dr. Zhu and Dr. Liu are working on the nonlinear acoustics. In particular, they are very interested in the parity-time-symmetric acoustic problem. Okay, now. Essentially, the group led by Dr. Zhu and Dr. Liu has been focusing on acoustic metamaterials as the parity-time-symmetric acoustic, or in short, PT-symmetric acoustics. They theoretically proposed and experimentally demonstrated a passive acoustic PT-symmetric structure which shares similar underlying physics and scattering properties with an accepted PT-symmetric system, but their idea is free of a gain medium. The structures they developed is realized via 2 types of acoustic metamaterials that respectively modulate the effective refractive index in the complex plane, which can provide unidirectional wave vectors at an exceptional point for balanced, real, and imaginary part modulations. So it is thus unidirectional reflectionness and supportive reflective focusing on the other side. Another major area is on the chirality reversal radiation in PT symmetric ring cavity. Okay. Basically, in this work, they revealed that a counterintuitive phenomena, in this part of the work. What is the phenomena is? The phenomenon is that the excited sound wave can exhibit completely opposite chirality to the coalesced eigenmode. The eigenmode, that is the acoustic wave. It means that the acoustic wave does not propagate in the way indicated by the system eigenmode, which means the radiation field of the source can become fully decoupled from the eigenmode of its surrounding environment at an exceptional point. And the chirality reversal phenomena they observed was theoretically investigated and experimentally confirmed, and it can be applied to the generation of acoustic waters with controllable chirality. Now, this area is pretty advanced and at the forefront of acoustics, acoustics research, and this is the getting hot. Okay, this time the topic is getting hot, and you can see that our our team has been advancing ourselves. Okay, make sure that we are staying with the state-of-the-art development in the sound and vibration research. Okay, then come to the next area in the some research area in the building acoustics and vibration, which appear to be more practically biased. Okay, now and this area, okay, this slicer, okay, comes from the CM mark, and from the building services engineering department of our university of Poly. Now he has a three major area. Okay, right now the first one is on the prediction of a flow-generated noise from multiple induct elements in a ventilation system. And Professor Mark made good use of some of the combined theoretical and experimental study, okay, on how the aerodynamic sound is generated from the multiple spoilers in the air ducts. Okay, those spoilers are mainly installed for controlling the flow rate within the air, the ventilation rate, and then he developed a simple prediction methods that could be used together with the information available from the CFD. He is also looking at the noise control in the duct based on an array of Helmholtz resonators. Okay, so that's with a different resonators design put together on a duct to achieve a remarkable transmission loss. Okay, he made extensive use of a finite element method as well as the constant multiphysics. Okay, for the evaluation. And he is also working on developing methods for assessing the performance of vibration isolator of various building services equipment. Essentially, this power is based on the power transmissivity method, and so that's for the evaluation of the performance of a steady and transient vibration isolation. Okay. And then through the analysis of the coupled flexural longitudinal wave motion in periodic dual-beam structure, okay, he then move on to propose a kind of adaptive passive vibration isolation between non-rigid machines and non-rigid foundations. Okay, using a design with dual-beam periodic structure. Okay, so you can see that's apart from the staying a breeze from the forefront of sound and vibration research, we also don't forget the really practical sound and noise and vibration problem that our good industrial partners are facing. And then this is another research, that is more practically biased, and the area is in the environmental acoustics, and I'm responsible for leading this effort in this area. Essentially, the major focus of this area is the environmental noise, that we are suffering in Hong Kong. Now, and previously, I showed you several very beautiful pictures, about the Hong Kong night scene. And right now, I change another angle. If we wheel from the sky and look towards the ground, you can see that our cities are really full of tall buildings, and the buildings all together create a kind of street canyon environment. And between the buildings, we have many roads. We have a very busy traffic, so that the environmental background noise level is pretty high. And traffic noise is the major contributor, of the environmental noise problem in the Hong Kong city. So our government, has been constantly trying hard to reduce the nuisance, for this traffic noise. And certainly, if you want to do a good noise control, you need to measure the traffic noise. I mean, have a good information from accurate traffic noise measurement. And for this purpose, we developed the close proximity technology, okay, for the high road noise measurement in Hong Kong traffic. Now, basically, that CPX technology is specified in an ISO standard 11819-2, okay, which involve the use of two microphones, which are placed very close to a rolling time, so that we can see how the noise level grow, okay, or changes with various vehicle speed and various road surface design. Okay. Now, as you can see, we already developed a kind of a prototype, from the lorry and the CPX chamber, okay, shown in the bottom. And recently, we have advanced, okay, the design of this CPX chamber with a numerical model, so as to get a much suppressed background noise within the CPX chamber for more accurate traffic noise measurement. And we were able to reduce, okay, the background noise level by 3 to 5 dB, okay, which is pretty much as compared to the variation of the traffic noise. And we believe that with the outcome of this research project, we are able to measure the level as well as the spectrum, okay, of the high road noise at the different type road surfaces, okay, different vehicle speed, different loading, okay, so that we can easily get a better understanding of the traffic noise climate, okay, in Hong Kong, so that we can prepare government for some effective changes. Okay. Now, so that is the end of my presentation. I hope that my presentation have given you a broad idea, okay, of various research activities at the CSVR. And if you're interested, okay, in any one of the research projects, you can simply write me an email or an email to Professor Chen, so that we can have a further discussion and possibly fruitful collaboration. So allow me to say thank you for your attention and wish you stay healthy and have a good day.